Welcome everyone to the first lesson of the course General Relativity for Betas. So, in this first lesson, we'll see what's index notation and also we'll learn about Einstein's summation convention. And we'll also develop some notion about what are free and dummy indices. So, to begin with, I decided to show you a somewhat scary formula at first, so jump scare alert. It's this one. So, these are Einstein's field equations, and yeah, they're equations, as although we have one single expression, this is actually more equations. They are compactified into just one formula. So this is done thanks to index notation, and if you have seen many formulas in general relativity, you'll have noticed that there's a pattern that repeats, and it's that these little guys here, small Greek letters, they appear all the time as indices, whether they are down or they can also be up. And we'll see the difference between up and down in later lessons. But what I want you to know for this lesson is that we can compactify various equations in just single one expression thanks to index notation. So let's begin to learn index notation, but of course with a simpler case. We are not going to start learning it with Einstein's field equations. So I'm going to write a formula that I'm sure you'll all know, which is Newton's law of dynamics. So this is obviously in vector notation, as you may see of those little guys standing up there. And you can see a resemblance between this formula and the Einstein's field equation, and it's that this is not one formula, these are three. Because if we are working in ordinary 3D space, what we are really saying with this formula is that the x component of the force is the mass times the x component of the acceleration, and the same for the y component, and the same for the z component. So the vector notation does a great job by compactifying some equations into a single one. And now we are going to jump to what will it be this equation in index notation. So in index notation, we may write this equation as f sub I equals the mass times a sub I, where I is our index, and we are going to define it obviously, which is an index that runs from 1 to 3. And we can make the identification of 1 with the x component, 2 with the y component, and 3 with the z component. Thus, if we write like something like f2, what we are really meaning is the y component of f. Or also a3 is going to be the z component of a. Thus, by making this identification, if we write this formula for the three values of I, we recover these three equations. So this formula is just equivalent to the other one, and you may think, well, why do I need index notation? I have gained nothing. I mean, it's even more beautiful to write it with arrows instead of indices and all this. And this is the reason why index notation is not commonly taught at some basic level, because it's really useful for more advanced topics such as general relativity, and also it's used in quantum field theory and other advanced fields in physics. But in order to learn index notation, it's better to start with these simpler scenarios. And let's see, for example, another equation. So the rate of change of work or energy, we may write this as the dot product from the force and the velocity. And this equation is different from the previous one in the sense that this equation of Newton's law of dynamics, they are three equations, as we have seen, because they involve vectors. And these vectors, they are free in a sense that, for example, in the left-hand side, there's just a vector. And in the right-hand side, we have a scalar, which is a scalar is a number. We have a number multiplying a vector, and all this is still a vector. However, in this equation, we have the dot product of two vectors. So the dot product of two vectors is just a number, it's not a vector. And also the left-hand side is just a number, it's not a vector. So this is one equation. Although it involves vectors, these are not three equations compactified into one, it's only one equation. So how can we write this in index notation? Well, we can develop this dot product into the x component of f times the x component of b and we do this for the other components. And we may say, hey, I remember the identification we made before. So we can write f1 times v1 plus f2 times v2 plus f3 times v3. And now that we have numbers, you may say, oh, I can write this into a sum. And this is a very decent compactified way to write this with indices. So is this index notation? Not quite. It's almost index notation, because we have to introduce something which is very important, which is Einstein's summation convention. I'm going to write it explicitly. And I'm not going to write these definitions along the course many times, but this is a very important definition. In fact, it's, in my opinion, the most important one in index notation. So I'm going to write it explicitly, and I'm going to highlight it in bright yellow so that it sticks to your head. So what's Einstein's summation convention? Einstein's summation convention says that if we have two repeated indices, they are summing. So what does this mean? We are going to take this with an asterisk, and we are going to put that this is very important. This means that we can write, give me a second, okay. So Einstein's summation convention says that if we have two repeat indices, such as in this case, and they are summing, we may omit the big sigma symbol, because the fact that we have two repeat indices, it's implied that they are summing. Thus, we don't need to write this symbol. So in index notation, this formula would look just like Fi Vi. So it's very compactified. It's the same length as with the vector notation. So we are seeing that it's also a very decent notation for the dot product. And I want to also remark what I have said before, that this equation are three equations and this is one equation, and this leads us to another concept, which are free and dummy indices. So what's a free index? A free index is an index that when you give values to that index, you get more equations. For example, in this equation, if you give values 1, 2, 3 to the I index, you get 3 equations. So giving values to the index gives you like more information. It spits out the equations. However, here in this formula of the work, this index is not free, it's summing. And remember the Einstein summation convention, there's really a big sigma before this expression. So this index is summing and it's not free. You can't give values to that index because it's embedded in a sum. So you don't gain new equations by giving values to the I, and we call this a dummy index. So I hope you see the difference between free indices and dummy indices. We'll see more examples in more equations in later videos, but this is like what's the notion of a free and dummy index. We may see another example, and we can take Gauss' law of electrodynamics, which is that the divergence of E equals rho over epsilon 0. So the divergence of E is simply partial x Ex plus partial y Ey plus partial z Ez. Now we may recall the identification we made previously, and we can write this as partial 1 E1 plus partial 2 E2 plus partial 3 is 3. And now we can write this as a sum. And by Einstein's summation convention, we have two indices which are summing together. We may say also that they are contract together, because when two indices are summing, we can also say that they are contracted. And contract indices are dummy indices, as we have seen before. And we can omit this sum symbol. So this is directly, by definition, del I EI. And go slow in this index notation. This was vector notation. And in index notation, it will take this form. So this is another example where we have a dummy index, which is here, the I, it's contract, and both indices are contract together, they are summing, and they are not free. In fact, this is only one equation, again. So, and you can see the relation between free indices, more equations, and dummy indices, contractions and dot products. And also we have seen that we may use the index notation for derivatives, and this is going to be very useful in later videos, because it's going to allow us to derive many formulas for vector calculus, which are somewhat very difficult to derive in vector notation, but in index notation they are very easy. So, and far in other videos we'll see how it's really a good choice to treat partial derivatives as this with index notation. So, I hope you enjoyed this lesson. If you have any doubt, you can write in the comments, or any suggestions about the videos, how they are made. See you in the next video. Bye.